Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will continue with the sound absorption mechanisms. So, it is actually the mechanism for porous materials that we have already discussed in last session. This is by the friction loss, then momentum loss and temperature fluctuations. So, in a porous medium, when sound penetrates inside, so frictional loss takes place, momentum loss and temperature losses. Apart from the porous medium, we have the different types of surfaces are there. So, one is the non-porous surface, that also affect the sound absorption. These surfaces reflect most of the sound and back to the environment. So, non-porous surface and leading to minimal absorption. So, in case of porous material, so sound penetrates and gets absorbed, but here most of the sound gets reflected. So, absorption is minimum. This is the non-porous surface, and the porous surface, this surface allows the sound wave to enter into the material and increasing the likelihood of the probability of internal reflection within the structure, energy transfer to the fiber or solid matrices through the frictional loss, that which happened in case of textile material, and greater overall absorption efficiency. So, porous surface, if it is there, then it can penetrate inside. Okay. If it is non-porous surface, it is flat surface, then most of the sound will get reflected. Here most of the sound gets absorbed. So, based on this all these principles, we can now measure the sound absorption capacity. So, acoustic measurement techniques are there. There are different techniques available that we will discuss one by one. The sound absorption behavior of a materials is generally measured using two standard techniques. There are two standard techniques are there. One is that reverberant field method, and second one is that impedance tube method. The two methods are there, we will discuss in detail. The sound transmission behavior of material is generally measured in two standard techniques. One is the 4 microphone transfer matrix method using the impedance tube. So, there will be 4 microphones will be used, and that 4 microphone transfer matrix will be there, and which is as per the ASTM E2611 method using the impedance method. And second one is that it is a 2 room method, that is reverberant method, field method. So, this room is known as reverberant room. So, two room method ASTM E90, it is also called reverberant room method. First is the reverberant field method. This is the reverberant field method, let us discuss. So, there is a reverberant room which will be there here, okay. Large size room. This method determines the absorption properties of material using reverberation chamber. That chamber is there, where the specimen will be kept. This is the specimen, green color is placed on the room. So, in the room the specimen is placed in a certain place, and the reverberation time are measured here, like as we have discussed RT, the source will stop generating the sound wave and the time will be measured, where the sound, the decibel of the sound is till the it is a 60 decibel is reduced from the initial time. That time we have already discussed, reverberation time, with and without the material under identical condition of temperature, humidity and everything. So, first we will measure the reverberation time with material, and then we will remove the specimen, and then again in the same room, keeping everything remains same, we will measure. And reverberation time RT 60 is the time required for the sound to decay by 60 decibel in an enclosed space after the source stops, that we have already discussed, reflecting the live, okay, that is a long reverb or dead short reverb at a how much live or dead the room is, that so the measurement of the this that type of room or type of material is there. So, materials reverb this method is used to test the materials sound absorption capacity. And here if the initial reverberation time is T1 and without the specimen, and after the specimen is placed, the reverberation time is reduced to T2. Initially it was T1, then it is reduced, it is because it is absorbing. So, sound is actually absorbed fast, that decibel is reduced. So, after the material is placed, it has reduced to T2, then the from this difference the effective absorption area delta A of the specimen can be calculated using the following the relationship. This is the relationship. So, effective absorption area is 55.3 by V by C 1 by T1 minus 1 by T2. T1 is the initial reverberation time and T2 is the when the sample is placed, C is the speed of sound, V is the total volume of the chamber, and from there we can calculate the sound absorption coefficient alpha, and it is obtained by . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . delta A by S. Delta A we have calculated, which is effective absorption area, and S is the area of the room covered by the sample, that is the sample area. So, from there we can calculate the sound absorption coefficient by using the reverberant field method. So, effectively sound absorption is the absorbed energy by incident energy. So, there are some guidelines are there for this type of test. The guidelines are the sample area S should be at least 10 square meter, that will be a large area, 10 square meter area should be there, sample area. If it is small sample, then the problem will be there that T1 and T2 with and without the sample, the reverberation time difference will not be significantly different. The chamber volume V must be greater than 4 lambda, where lambda is the longest wavelength to be tested. So, that accordingly, so wherever the longest wavelength 4 times to that, smallest chamber dimension should be 2 lambda. So, this one side will be that one chamber dimension should be 4 lambda, and smallest it should be 2 lambda. Ratio of the largest and smallest dimension should not exceed 2:1, that ratio should be there. This method simulates diffuse sound field and provide absorption data. So, this is actually it simulates the diffuse sound field and provide absorption data, that is representative of real environment. So, whatever we test in the space in the instrument, that will give some data, but here it will be the real environment is created, and from there we calculate the absorption. Next is the impedance tube method for sound absorption measurement. So, in this impedance tube method measures normal incidence sound absorption coefficient SAC by confining the plane sound wave into the cylindrical tube. In earlier case that sound is actually not been confined, here we try to confine the sound wave into the cylindrical tube, standard cylindrical tube, and here the small sample specimen is required. Earlier case the specimen size was 10 square meter, but here specimen size is very small, maybe 30 millimeter diameter, or sometimes we use 100 millimeter diameter, 30 or 100 millimeter. Small size sample is test specimens are required, and here we use in impedance tube we use two techniques are used. One is the standing wave ratio technique, that is ASTM C384 method. Another is that transfer function method ASTM E1050. So, standing wave ratio method and transfer function method. So, these two methods we will discuss now. So, impedance tube using standing wave ratio method. What is that? Now, you can see here. Here it is actually it is also known as the movable microphone method. This microphone is movable, we can move this microphone using this carrier. So, there is a microphone is moved, okay. This is a microphone and here loudspeaker which generates the sound. So, standing wave method, here it is also known as the movable microphone method. Now, the entire setup is that a loudspeaker is there placed at one end of the tube. There is a tube is there. So, at one end the loudspeaker is placed here which generates the sound. This loudspeaker generates the, while the specimen is mounted at other end. This is the test specimen, okay. And a rigid that is termination will be there, it will be a rigid plate will be there, rigid support, and this is test specimen is kept here. The incident and reflected wave are superimposed to form a standing wave pattern inside the tube. That is why this is called standing wave ratio method. So, here incident wave and reflected wave, they will be superimposed, okay, to form the standing wave pattern. And here the microphone is moved, the movable probe microphone measures the standing wave pattern formed by the superimposition of incidence and reflected sound wave. So, as it is moving, they will actually there will be superimposition, that pattern will be recorded by the microphone, that pattern of the standing wave, okay, as they are superimposed. And by moving the probe along the tube, the system detects the maximum and minimum pressure value. So, there will be superimposition and that will create the maximum and minimum pressure value, and due to this movement, while moving it will detect the maximum and minimum pressure value, and that will be recorded. And that is, from there we can calculate the standing wave ratio, SWR is calculated, which is for maximum sound pressure by minimum sound pressure. And then sound absorption coefficient is measured from this standing wave ratio using the relationship. This is the following relationship is there. If the n is the standing wave ratio, so sound absorption coefficient can be expressed as 4n by n minus 1 square. So, from there we can calculate the sound absorption coefficient, okay. By moving the probe we can calculate we can measure first the standing wave ratio n, and from there we can calculate the standing sound absorption coefficient. And another method of through impedance tube, that is transfer function method. One was that standing wave ratio method, and here the transfer function method. So, here we use two fixed microphones positioned along the tube. So, this is a two fixed microphones. Earlier case there was a movable microphone, and transfer function method, here there are two microphones 1 and 2, and loudspeaker produce the sound, the broadband and stationary random wave. So, broadband stationary random wave sound that is created by loudspeaker, and a two channel frequency analyzer records the complex transfer function H, from which reflection and absorption characteristics are computed. So, complex transfer function, from that they measure the reflection and absorption characteristics. So, transfer function method. So, the reflection coefficient R is determined using the relationship. This is the relationship, complex function. So, this is the relationship. We are not going into the derivation here, but our idea is not to just to understand the test method. So, where H12, H12 is the complex 1 and 2, this 1 and 2 is a complex transfer function between microphone 1 and 2, and S is the distance between the microphones. Here the distance, this is the distance between the microphones. So, from there we can calculate the absorption coefficient also. This is the reflection coefficient R, and alpha is the absorption coefficient, and alpha is can be calculated by minus 1 minus R square. So, that way we can calculate the this absorption coefficient from the reflection coefficient, and by using the transfer function method, which is impedance tube method. So, impedance tube, we have seen that two methods are there, one is the by movable the microphone, and the stationary two microphones are there for measuring the absorption characteristics, sound absorption. Then also we can measure the sound transmission loss. One is the sound absorption that we have already discussed, where we can calculate we can measure the sound absorption coefficient alpha. Now, sound transmission loss also we can measure. So, sound transmission loss represents the sound insulation capacity of a material by quantifying how much incidence energy, is passes through it, that is how much energy is transmitting through the material, that is the sound insulation capacity. If there is no sound passing through, energy is passing, that means its the capacity, the sound insulation capacity will be better. And here we use two methods. One is by using the impedance tube, sound transmission coefficient also is measured by impedance tube also, which is called 4 microphone transfer matrix method as per ASTM E 2611, also by reverberant method, room method. This is by 2 room method, which is ASTM E90, where we need to measure the transmission. Now, here you can see when we are talking about the transmission, we are not intending to get it reflected. Okay. So, we want that sound should get transmitted, and how much it is transmitting, that we will measure. So, here this is the specimen in the impedance tube method. The sound is actually the loudspeaker generates the sound, and here there are 4 microphones. So, microphone 1 and 2, which will take care of the whatever sound is absorbed or whatever sound is the reflected, that it will take care and it will measure, and then the microphone 3 and 4, this will also measure the whatever sound gets transmitted through the material. So, that it will measure, and here anechoic termination, after that no sound will pass through this material. So, here by this ratio we can calculate the sound absorption transmission loss. So, similarly, in the reverberant room also the sound is generated here, and between the two room method, the specimen is kept, and whatever sound is moving in the next room, that is also measured here. Okay. There will be microphone, so that will measure the sound. These are the methods. So, here what happened, here we measure by the directing the sound onto a specimen and recording the transmitted sound pressure using the microphone in the opposite side. Here we measure the sound pressure. Similarly, here in the 2 room method also we measure the sound pressure in the other side. So, from there we can calculate the sound transmission loss. So, knowing both incident intensity and transmitted intensity, we can calculate the sound transmission loss by this relationship. So, STL, sound transmission loss, equal to L1 minus L2 plus 10 log AS by AE. What is L1? L1, L2 are the space averaged sound pressure level, okay, and AS and AC are the area of the specimen and equivalent absorption area. Okay. Alternatively, sound transmission loss may be expressed as sound transmission loss is equal to log 10 log 1 by tau. Tau is that is the transmission loss by total energy. So, this way we can measure the sound transmission loss using both impedance tube method or 2 room method. Now, if we compare both impedance method and other method, like sound absorption is measured using 2 microphone transfer function method, which is impedance tube method, where this follows ASTM E1050, ASTM C 384 and ISO 10534 -2, this method it is used, that is sound absorption, and as compared to that reverberation room method, it is actually using the ASTM C423 or ISO 3454. This method it is used. Using the sound to measure the sound transmission. So, if we use the impedance tube method, we have used that 4 microphone transfer matrix method is there, which is ASTM E2611, and if you want to measure sound transmission using the reverberation method, it is a 2 room method is used using ASTM E90 method. The advantage of this impedance tube method is that we need very small size of specimen, 30 millimeter or 100 millimeter, 30 millimeter or 100 millimeter specimen, small sample size, and we need very less space. Within a tabletop we can test, and measurement time is very short. So, quickly we can get result, but in the reverberation room method, random incidence acoustic measurement is there. So, here in impedance tube we have some standard method, just this is not actually, it does not simulate the actual condition, random incidence is not possible, but here in the reverberation method, 2 room method or any reverberation room method, random incidence acoustic can be measured. So, we can generate the actual situation, simulate the situation, and broad frequency range that we can use here, a limited edge effect because of the large volume, limited edge effect is there. And the disadvantage of impedance tube, it is only normal incidence acoustic measurement is there, and it has limited frequency range. In case of this reverberation room method, broad frequency range, here limited frequency range can be used. Adverse effect of mounting condition, sample edge effect is there, but here mounting is not there, sample is simply kept. So, edge effect is limited here. The disadvantage of the 2 room or reverberation room method is here large specimen is required, large sample size and huge space requirement, and here we need longer testing time, very long testing time required. So, looking at this advantage and disadvantage, we can select our test method depending on our requirement, but both the systems are used. Now, we will discuss the different types of materials which are used for sound absorption. The materials may be open cell foams, fiber board or panels. These are most commonly used sound absorbing material, commercialized. These are the foams and fiber mats are used. Various natural and synthetic fibers are used for sound absorption, among which the mineral fibers based boards or panels are commonly used. So, different mineral based fibers are used. Now, the textile structures for sound absorption. So, we can use that the textile for as a composite material. For this composite material is basically made of natural or synthetic fiber and using the matrix, polymeric matrix we can use for sound absorption. So, these are used for sound absorption and damping, and these are the rigid structures. So, composite structures are rigid structure we can use as a sound absorbing board, okay, sound absorption and damping. Then nonwoven structures are used, nonwoven fabrics, these are used basically mainly for sound absorption because of the porous structure, and this perform better in high frequencies. So, nonwoven fabrics they perform for high frequency, for absorption we can use nonwoven fabric, and the advantage is it is lightweight and it is cost effective. We can use a needle punch nonwoven, nanofiber membrane also used, we can use different types of combinations, even spun bonded is used, melt blown is also used. This all this we will discuss when we will discuss different studies, research studies we will discuss. Knitted structures are also used. So, normal knitted fabrics or spacer fabrics are used here, used for sound reflection and dampening. So, nonwoven is used for sound absorption, knitted fabrics are used mainly for sound reflection or dampening, okay, and perform better at lower frequencies, and nonwoven performs better in higher frequencies and used for absorption. Here knitteds are used for reflection and for lower frequency, and these are durable structure because these are some directly it is a some structured form it is used like in knitted fabric form, and woven materials are actually similar to knitted, used for sound reflection and dampening and most durable structure and perform better at lower frequencies. So, and 3D oven and 2D oven are different types of weave structures are used. So, both knitted and woven fabrics are used at for lower frequencies, it performs better, and used for sound reflection and dampening. But on the other hand, nonwoven is used where sound absorption is required, we need to absorb sound, and where high frequency is there. And now we will discuss the materials and physical properties which affect the sound absorption. So, different studies we will discuss, and before that we will let us see the different types of materials and physical properties which affect the sound absorption. For any porous material, the sound absorption is primarily affected by thickness and its air flow resistivity. So, if the thickness is more, the sound will get absorbed more. Okay. Now, however, material and physical properties also affect the absorption, especially medium to high frequencies. The physical properties are there. Now, these are the fiber properties. So, we have the fabric properties also. First, let us see the what are the fiber, how the fiber parameters affect the acoustic property. Now, fineness of fiber. So, sound absorption coefficient improves with an increase in fiber fineness. If the fibers become finer, this is the coarse fiber, and if the fibers become finer, sound absorption will be more, because as the fiber fineness increases, the surface area of the fabric increases. The fiber surface area, effective surface area of fiber, which is resisting the sound wave, it will increase as compared to the coarse fiber. So, overall surface area increases, there will be friction loss, more and more friction loss, and heat energy loss will be there. So, with a greater surface area, friction loss increases, and also as the fiber become fine, they will be more flexible. So, they will actually take the wave, they will absorb the wave, wave will not get actually reflected. So, finer fiber will take the moment, reduce the momentum of the momentum, there will be momentum loss. So, one is the friction loss, and momentum loss will also be there, and due to that the sound absorption will improve. Next is the length. Effectively, length does not have that great effect on sound absorption, fiber length. So, increase in fiber length enhance the sound absorption coefficient little bit, but however, the effect is usually insignificant below that 1 kilohertz limit. Okay, that is that effect is not that much significant. So, we can take the advantage of this fiber length at higher frequency level. So, high frequency only we can get this advantage. Third is the cross sectional shape. Cross sectional shape has got significant impact on sound absorption, because suppose the circular and there is a trilobal. Here the surface area for same linear density, surface area will of the irregular shape, trilobal shape is much higher than the this circular one. So, that higher surface area means higher frictional energy loss. So, that higher absorption will be there. So, for that reason that cross section has got significant effect. So, fiber cross sectional shape influence its sound absorption behavior. In a study on fibers with different cross sectional shape, fibers with irregular surface or cross section shows better sound absorption, basically due to the frictional loss. So, this is due to the higher increased surface area resulting higher frictional loss. So, here frictional loss will be increased. Percentage of binder fibers. So, in the bicomponent fiber, or maybe the mixture of low melt and that is binder fiber with a normal fiber, if the percent of binder fiber increases, that means structure become stable, there will be stable structure. So, there will be stable structure, a pore structure will be stable, there will not be that much distortion of the pores. So, an increase in proportion of the binder fiber enhance the sound transmission loss. This effect is likely due to the increased stiffness of the nonwoven structure as binder fiber content rises, which improves the ability to resist the sound wave penetration and dissipate the sound energy more effectively. So, transmission loss, that will be that it will dissipate the sound energy. Next is the crimp. Crimp means it is creating the pores in the structure. So, fiber crimp enhance the sound absorption because of the higher pores due to the creation of small pores and reduction in fiber grouping. So, there will be pores will be there, and without crimping there will be fiber grouping. So, these pores are required, as we have already discussed. Sound energy should enter into the pores, there it should enter into the pores, and there the frictional loss will be there. Not only frictional loss, there will be inertial loss will be there, okay, and momentum loss. So, due to the uneven pore, there will be momentum loss also. So, crimping or texturing has a very significant impact on sound absorption of yarn based fabric like knitted or maybe woven fabric. So, if we use crimped or textured yarn, there will be significant improvement in sound absorption behavior. Next is the fabric parameters. First is bulk density. So, bulk density has got significant impact on sound absorption. It is the volumetric density or total mass of the porous material per unit volume. That generally high bulk density results higher sound absorption due to higher fiber and air interaction. That means, here if you have pores in the structure, so high bulk density, that will result that there will be fiber and air interaction will be there, because the number of fibers will be there and the pores are there, but number of fibers will be more. So, when the sound penetrate into the porous structure, the more and more obstruction it will be there. So, more and more friction will generate and higher energy loss, that heat loss will be there. So, that but if we keep on increasing the bulk density, that what will happen after certain limit, further increase in bulk density results reduction in absorption due to higher reflection. So, if the surface is very compact, there is a very compact surface, bulk density we have increased great. So, there will be very less pores within the structure. So, that sound will not be able to penetrate inside, it will simply reflect back. So, the higher reflection will be there, so sound absorption will be less, okay, reduced absorption. So, there is a optimum value, optimum range will be there. Next is the thickness. So, thickness has got significant impact on the sound absorption behavior. As the material thickness increases, the path of the sound wave needs to cross a increased area. that is important. So, if you have say this is a lower thickness and another here is a larger thickness, this is the material, and when the sound wave is penetrating, it will have some action, that is friction loss whatever may be, but the some of the sound will not be absorbed, but that will get transmitted. But if the thickness is larger, sound wave is penetrating, it will start interacting with the fiber, and during this path there will be viscous loss will be there, more and more viscous loss will be there, because during the transmission they will interact with the fiber, there will be loss in energy due to the friction and other different ways of that is the momentum loss will be there. So, that is called the loss in viscous, this is the viscous loss will be there, and more absorption will take place. So, the thickness also drives the surface impedance of material by manipulating the frequency of interference. So, a porous material should have a thickness of at least 1/4 of the wavelength of the sound. So, which it intend to absorb. So, that is the typical standard, the thickness should be at least 1/4 of the wavelength of sound. So, that type of thickness it should be there. Next is the porosity. So, porosity is also it affects the sound absorption like a bulk density. So, this has got similar effect to the bulk density with the decreasing porosity, that means it is becoming compact, okay. Gradually decreasing porosity, the sound absorption increases initially because of the creation of more and more fibers obstruction, but too low porosity, that means if the bulk density is very high, it may result higher reflection and less absorption. It is just inverse, porosity and bulk density, they are basically affected, say their effects are exactly similar, but in the other way, reverse way. That means higher bulk density means lower porosity and vice versa. Along with porosity, pore shape and size also affect the sound absorption of the material. That is very important. Pore shape and size will be important, because suppose we have two material with the same porosity, this is material A and material B. Material A has the pores, material A has the pores of larger size. So, larger size pores are there, but material B will have the smaller size, but total volume, but the material B will have total volume of pores are same, but with a smaller size pores, with large number of pores. Smaller pores with a large number. If we calculate the porosity of both this fabric A and B, they are same, but when the sound penetrates, sound enters, the behavior of sound absorption will be entirely different with the pore size and pore shape. So, sound absorption will be different for these two fabrics depending on the shape of the pore or size of the pore. And next is the tortuosity, which is also important. The pore may be straight or pore may be tortuous pore. This tortuosity described how nonlinear the pores in a porous medium. Suppose there is a two fabrics are there, this is two fabrics. One fabric has got straight pores, another fabric has got the pores like this, tortuous pores. Okay. These are two pores are there. There is a two distinct pore, here there are three pores suppose. Now, this is the straight pore, here is tortuous pores. So, this non-linear pore will have effect, great effect on sound absorption, because it will sound will travel and the sound wave will strike or interact with the fiber material. In a material with higher tortuosity, sound wave have to travel through a longer path through the fibers, and it will cause more frictional or viscous loss. It will lose its energy through the frictional loss or through the heat will be generated. But on the other hand, if it travels through the straight pore, there will not be that much restriction, not the frictional or viscous loss will not be there. So, among these two, the fabric with higher the tortuous that pores will absorb more sound, the sound absorption will be more in case of this tortuous pore than the straight pore. So, that is the reason in case of non-woven fabric we have this type of pore, tortuous pores, or in case of woven we have typically straight type pores. So, non-woven fabric is used for mainly sound absorption, and in case of woven fabric the sound absorption is less. So, we have understood the different types of different parameters which influence the acoustic properties, the fiber parameters like length, diameter, cross sectional shape. Okay. In case of fabric, the parameters are the bulk density, thickness, pore structure, tortuosity. So, that we have discussed, porosity, and how they are actually affecting the sound absorption, and then there are different noise protective textiles are used, and that this all this and further different factors affecting the noise transmission characteristics, noise absorption characteristics, those we will discuss in next session. Till then, thank you.